Welcome to the Valor Division's webinar on process engineering and the single point of truth. This is a follow-up of the process preparation webinar we posted last month. My name is Mark Lane and I have been in the process preparation team of Valor for over 10 years. I thank you for attending and will be giving you a more detailed look at our process engineering solution. I presented last time on the challenges of creating PCB assembly collateral, and they all drive the need for a single point of truth. If everyone programming the PCB line is using different software and different source data, how can we expect that we will get consistent and correct data flowing to all steps in the PCB assembly process? Let's take a journey through all aspects of PCB assembly collateral creation using Valor process preparation. Regardless of the electronic product being built, there is a common data set that drives all of the assembly processes. The PCB itself, the bill of materials or BOM, the components that are placed on the board, the schematic data that was used to create the layout, and if the board is panelized or not. All of this information is common across the assembly equipment. Some of it needs to be transformed to be accepted by specific machines, but nevertheless it is still based on the same common data. Let's look in more detail of a complete data set that exists in Valor process preparation. One of the challenges using a single application for data preparation is that the software does not support all of the required data for all tasks. SMT and inspection programming don't read a netlist. Test programming doesn't read paste data, for example. Valor Process Prep creates a complete digital product model, as we shall now see. Let's open a complete project in Process Prep and see all the elements we just described in the complete digital product model. First, we see the board itself, which is usually created from some form of CAD import. However, it can also be created from Gerber files, provided they are processed through component extraction and netlist derive functions, both supported by Process Prep. Each PCB layout will have been created based on a schematic design. This schematic data is critical to electrical test, providing additional data not typically delivered in the physical layout, namely pin functions, such as anode and cathode, or base collector and emitter. Next, we see an assembly, which is a board with a bill of materials file. The BOM describes which part number is placed on which component position, and those that are not placed on a specific variant. The BOM can also specify the manufacturer and manufacturer part numbers for all approved vendors. It is this data that we use to download the Valor Parts Library, or VPL data from the cloud. VPL gives us exact geometrical shape data, including height, for each part on the board, including alternates. As Process Prep can support the AVL data, there is a specific check that highlights any manufacturer part that falls outside of the tolerance of the component. This gives confidence that all alternates will fit on the board at an early stage instead of during first article runs, just prior to production starting. It is common for PCBs to be assembled with more than one at a time. These panels can be in multiples of a single board or a mix of different boards. Either way, Process Prep supports all manner of panels in its data model. With 70% of manufacturing defects being solder related, getting the right stencil in place is critical to managing the defect spectrum. The Valor Stencil Design module puts reusable rules in the hands of process engineers to better manage their stencil design process, as we shall now see. Stencils are typically created in a couple of ways. Either send your stencil guidelines to the stencil vendor, who then implements them for you, or resort to editing Gerber apertures across the whole board. In Process Prep, we use the intelligence of the design data to apply rules to each unique footprint. These rules can then be reused on future boards with the same footprint. Default settings are used across all footprints, but then footprint-specific apertures can be applied, as can part number-specific apertures. Parameterized standard symbols can also be applied to any footprint in the following manner. Select the pin or pins you wish to apply the standard symbol to, and then use the symbol replacement to completely replace the existing one with a new one. Special symbols can also be used for more complex shape requirements. Once complete, the resultant stencil can be exported to ODB++D or Gerber 274X. Furthermore, the same file can be used to export to a number of solder paste inspection machines. Management of position and rotation issues on placement and inspection machines is traditionally a cause of problems during first article runs that can be addressed with the overall placement and part library management capabilities of Vala Process Prep that we will see now. With the recent trend in single vendor SMT lines, optimization and balancing have become more the focus of the vendor software. However, this has also given way to mixed vendor factories that raises the challenges of part data management. Without process prep, there is no way to manage all the various part data libraries that are needed across multiple SMT lines. Process prep provides a unique way to use the machine-neutral packages directly through the ODB++ P format, or transform them into machine-specific data that can then be loaded directly onto the machine. Let's look at the part data management capability in more detail. It provides significant value for our customers over solutions that just point to the machine library for part data. In Vala Process Prep, we can import and create machine-specific part data based on machine-neutral packages. So if you have a machine library in one vendor format and want to use that data on another machine format, Vala Process Prep can do this. That is what you are seeing here, a part being created in ASM format based on part data that was created in the Fuji library. An area that drives significant value in the process prep application is the virtual sticky tape. The machine part data is overlaid on the board to show the user how each placement will occur in a virtual way before the product runs down the line. This can completely eliminate the actual sticky tape run that is performed to check placement and rotation issues before a program goes into production. Once all parts have been verified in virtual sticky tape, we can then export to all machines in the line with a single button click. With the Move to Line capability, once a complete line is configured, moving that line to another completely different one is a simple drag and drop process. This action creates all the machine-specific data needed for the target line with a single step. After data preparation, assembly work instructions and documentation creation is the most common use for Vala Process Prep customers. Although the majority of the parts are placed automatically on electronic circuit boards, there is still a need to place some parts manually, and that requires documentation. Documentation creation takes the complete digital dataset and applies a predefined user-created template that describes the necessary assembly work instructions to it. This creates our document package, including, but not limited to, intelligent images of the board, color-coded drawings, images and hyperlinks that produce the resultant documentation. The resultant document package can then be deployed in a read-only manner to the shop floor. Test programming has been an area of significant enhancements over the past few years that will continue as we consolidate our test analysis capability into Vala Process Prep. Electrical test programming forms the next area we will cover. With a few exceptions, most products are tested either through flying probe, fixtureless test machines, or in-circuit test, fixture-based test machines. Although the techniques used are similar, these machines undertake these tasks in very different ways. The VPL data that forms the basis for common part and package information is automatically enveloped to create a keep-out area for each part on the board. This step on its own significantly reduces the preparation time that is needed for test programming. We can also see how the schematic data can be shown with both the layout data and the device list to make sure that the component parameters are all accurate. The schematic is synchronized to the layout or device list, making the location of each component instant, regardless of the number of schematic pages. Predefined test plans allow an initial assessment on the testability of the design that can then be tuned to maximize the available test locations. The philosophy here is to provide complete data to the analysis engine with user-defined parameters and let the software determine the available access. It shouldn't require significant manual analysis by the test engineer first to create a solution and then tell the software what to do. That approach does not reduce the time and effort on test engineers. Once the analysis is complete, the results are now reviewed together through the easy-to-use PCB navigation. Here, unplaced probes can be quickly reviewed and, if necessary, manually adjusted with a simple drag and drop. For further review and to share these results with designers, there are many types of standard reports that can now be easily created and then sorted or filtered in a spreadsheet application. The final step is to create the necessary machine-specific outputs that can be used to complete the test programs in the machine software. As electronics assemblers need to be agile in their ability to deliver products around the globe, source files are typically sent to the new location when products need to be produced in another factory. However, this means repeating the new product introduction phase again when this work has already been completed once. The rationale for this is necessary as the machines are different, but coming back to our single point of truth that we started out with, we should be able to deliver this complete digital data model to the target factories. Process Prep can create a single container of common digital data as a portable product file. Just export the file directly from Process Prep and deliver it to your target site to build the product based on the work that has already been completed. Once imported to the new location, that site now has a head start in programming their line where they can output to their machines and create documentation using their template. All of the created collateral can be pushed back into Teamcenter and managed from there in a multi-site environment. I'll now hand over to my colleague, Kobe Levy, who will continue this theme for the remainder of the webinar.
Hi everyone, my name is Kobe Levy and I'm a business development manager working for Valor, focused mainly on process preparation and its integration to Teamcenter. And this is what I will show you in this session today. I will use a short demonstration in order to show you the capabilities and value of this solution. In this demonstration, we are going to focus on a company which has 4 facilities around the world. In Italy, where it holds its R&D, in Mexico, China, and Romania. In the typical flow, with their siloed solution, when the designer completes his work in Italy, the BOM and ECAD are sent to all of the other facilities, and from this point on, each facility does its own data preparation and process planning. Of course, this is a non-lean way to perform this task and bears with it a lot of waste. You can see that the data preparation, which takes the majority of the time, is done separately in each and every facility, producing a lot of waste as it could be done once for all the facilities. After the data preparation is done, each and every facility does the machine programming and walk instructions authoring for its own lines. And if a problem occurs in one of the facilities, it is being handled only in this facility, and none of the other facilities knows about it and takes benefit of the fact that the facility in China, for instance, resolved this issue. So if the other facilities encounter the same issue, they will have to deal with this on their own, not knowing that the facility in China already resolved this issue. Now I will show a short demonstration that emphasizes the value of this integration. Here we see EasyPlan, and we can browse the work package. The work package includes the BOP, which is the routing, BOM, and the plant facility. In the screen, you can see the representation of the plant facility inside Teamcenter. The plant representation includes the work areas, lines, stations, and equipment that we have inside our plant. In the work package, we also have the bill of process, which is actually the route of operation. If we browse into the bill of process, we can see that we have two production lines. In the first line, the auto assembly and auto inspections are taking place. And in the second line, the manual assembly and the PCB test occur. Clicking on this button, EasyPlan invokes process preparation with the engineering data automatically loaded into it. And now the process engineer can perform the auto assembly planning and generate the NC files to send to the SMT machines. He can also plan the manual assembly operations and generate the documentation and work instructions to support these operations. The Stencil Designer can design the stencil while minimizing the number of iterations between the designer and the stencil vendor. The test engineer can also use process preparation to plan the test session and generate NC code for the test machines. In the end of the work inside process preparation, all NC codes and documents are ready to support the manufacturing of the PCB while assuring the desired capacity and quality of the PCB. Once the work is done in process preparation, the process engineer can export all of the collateral generated into the bill of process. Exporting this collateral is done in a way that assures that each operation stores its own collateral to support the right assembly in the operation, and it assures that the operation holds only the information that is relevant to the specific configuration of the PCB that needs to be assembled. On the screen, you see how we browse into the bill of process in Teamcenter and see that the ANSI files and documentations which were generated in process preparation are attached automatically to Teamcenter into the right operation. What we can see now is how the integrated solution works. With the integration to Teamcenter, the facility in Italy can perform the data preparation for all the other facilities and send to these facilities the prepared data rather than the raw engineering data. Each of the manufacturing facilities can now take this data and perform the machine programming and generate the work instructions to support the manufacturing in its own lines. This is a much leaner approach than working with a siloed solution. And if a problem or a non-conformance occurs in one of the facilities, it is no longer taken care of inside the facility. It is now taken care of in the central planning in Italy in an enterprise level. After this problem is taken care of in the central planning or R&D, the resolution of this problem is sent to all facilities, and they all benefit from an enhanced planning. In conclusion, you can see that the integrated solution can allow performing the process planning in a much more efficient way than a siloed solution, and it supports linear manufacturing approach.
Thank you for attending this webinar. I hope you found it interesting and informative, and that you will attend our next one. We will now open it up for questions.